Welcome. Today we're diving into the fascinating world of semiconductors and exploring a key concept known as doping. If you've ever wondered how your smartphone, computer, or any modern electronic device works, understanding doping is a great place to start. Doping is a process that transforms the electrical properties of semiconductors, making them the backbone of modern electronics. In this video, we'll break down what doping is, why it's important, and how it shapes the technology we use every day. Let's get started by understanding the basics of semiconductors themselves. Before we talk about doping, let's clarify what a semiconductor is. Semiconductors are materials that have electrical conductivity between that of a conductor like copper and an insulator like glass. Silicon is the most common semiconductor material. These materials are unique because their ability to conduct electricity can be precisely controlled. This property is what makes them so valuable in electronic devices. Now let's see how doping comes into play to enhance these properties. Their pure form, semiconductors like silicon don't conduct electricity very well. This is because their atomic structure doesn't have many free electrons available to move around. As a result, pure semiconductors are not very useful for most electronic applications. To make them more effective, we need to change their electrical properties. This is where the process of doping comes in, allowing us to tailor the material's conductivity for specific uses. Doping is the intentional introduction of impurities into a pure semiconductor to change its electrical properties. These impurities are called dopants. By adding just a tiny amount of dopant atoms, we can dramatically increase the number of charge carriers in the material. This process is carefully controlled to achieve the desired level of conductivity. Doping is essential for creating the electronic components that power our devices. Without doping, semiconductors would be almost useless in electronics. Doping allows us to control how easily electricity flows through the material. This control is what makes it possible to build transistors, diodes, and integrated circuits. In short, doping is the key to making semiconductors useful for building everything from microchips to solar cells. Let's look at how the process works in more detail. There are two main types of dopants used in semiconductors: donors and acceptors. Donor dopants add extra electrons to the material, while acceptor dopants create spaces or holes where electrons can move. The choice of dopant determines whether the semiconductor will have more free electrons or more holes, which in turn affects how it conducts electricity. Let's explore these two types in more detail. Type doping involves adding donor atoms such as phosphorus or arsenic to silicon. These atoms have more electrons than silicon, so when they are added, they donate extra electrons to the material. This increases the number of negative charge carriers or electrons, making it easier for electricity to flow. N-type semiconductors are crucial in many electronic components, especially in forming the basis of transistors. E-type doping is the opposite of N-type. Here, acceptor atoms like boron are added to silicon. These atoms have fewer electrons than silicon, creating holes in the atomic structure. These holes act as positive charge carriers, allowing electrons to move by filling the gaps. P-type semiconductors are just as important as N-type, and both are needed to create the electronic devices we rely on. By introducing donor or acceptor atoms, doping increases the number of charge carriers in a semiconductor. This makes the material much more conductive than its pure form. The amount and type of dopant can be precisely controlled to achieve the desired electrical properties. This flexibility is what makes semiconductors so versatile in electronics. Next, let's see how doping is actually performed in the lab. There are several methods used to dope semiconductors. The most common techniques include diffusion, where dopant atoms are diffused into the semiconductor at high temperatures, and ion implantation, where dopant ions are shot into the material using a particle accelerator. Each method has its advantages and is chosen based on the desired properties and application. Let's take a closer look at these techniques. Diffusion doping: the semiconductor wafer is exposed to a gas or vapor containing the dopant atoms. At high temperatures, these atoms diffuse into the surface of the wafer and become part of its crystal structure. The depth and concentration of doping can be controlled by adjusting the temperature and exposure time. This method is widely used in the semiconductor industry for its simplicity and effectiveness. Ion implantation is a more advanced doping technique. In this process, dopant ions are accelerated and shot into the semiconductor wafer at high speeds. This allows for very precise control over the location and concentration of dopants. After implantation, the wafer is usually heated to repair any damage to the crystal structure. Ion implantation is essential for creating complex semiconductor devices with fine features. The amount of dopant added to a semiconductor is called the doping concentration. This concentration must be carefully controlled to achieve the desired electrical properties. Too much or too little dopant can make the device perform poorly or even fail. Engineers use sophisticated equipment to monitor and adjust doping levels during manufacturing, ensuring consistent and reliable performance. Doping is a critical step in the fabrication of semiconductor devices. It allows manufacturers to create regions with different electrical properties within the same piece of silicon. These regions form the building blocks of transistors, diodes, and other components. By precisely controlling where and how much doping occurs, engineers can design complex circuits that power everything from computers to cars. Transistors are the fundamental building blocks of modern electronics, and doping is essential to their operation. By creating N-type and P-type regions within a single piece of silicon, engineers can build transistors that act as switches or amplifiers. The precise arrangement of these regions determines how the transistor behaves, allowing for the creation of powerful and efficient electronic circuits. Diodes are another important electronic component that relies on doping. A diode is made by joining N-type and P-type semiconductors together. This creates a junction that allows current to flow in only one direction. The properties of the diode, such as its voltage threshold and efficiency, depend on the type and concentration of dopants used. Doping makes it possible to design diodes for a wide range of applications. Degraded circuits or microchips contain millions or even billions of tiny transistors and other components. Doping is used throughout the manufacturing process to create the various regions needed for each device. The ability to precisely control doping at such a small scale is what makes modern microchips possible, enabling the incredible performance of today's computers and smartphones. Doping isn't just important for computers and phones, it's also crucial for solar cells. By creating N-type and P-type regions in silicon, doping allows solar cells to convert sunlight into electricity efficiently. The junction between these regions separates the electrical charges generated by sunlight, producing a flow of current that can be used to power homes and businesses. Light-emitting diodes, or LEDs, are another example of devices that rely on doping. By carefully choosing the type and concentration of dopants, engineers can create LEDs that emit different colors of light. Doping controls the energy levels within the semiconductor, determining the color and brightness of the light produced. This technology is used in everything from indicator lights to large display screens. Any types of sensors, such as temperature and light sensors, use doped semiconductors to detect changes in their environment. Doping allows these sensors to respond to small changes in voltage or current, making them highly sensitive and accurate. This is why doped semiconductors are found in everything from smartphones to medical devices, helping us interact with and understand the world around us. Power electronics, such as those used in electric vehicles and renewable energy systems, rely on doped semiconductors to handle high voltages and currents. Doping allows these devices to operate efficiently and reliably under demanding conditions. By carefully selecting the type and concentration of dopants, engineers can design power devices that are both powerful and energy efficient. As electronic devices become smaller and more powerful, the ability to precisely control doping becomes even more important. Advanced doping techniques allow manufacturers to create tiny features on microchips, enabling the development of faster and more efficient devices. This miniaturization has revolutionized the electronics industry, making it possible to fit incredible computing power into the palm of your hand. While doping is essential, it also presents challenges. Achieving the right concentration and distribution of dopants can be difficult, especially as devices shrink in size. Even small variations can affect performance or cause defects. Researchers are constantly developing new techniques and materials to overcome these challenges and ensure the reliability of advanced electronic devices. Future of doping technology is exciting. Scientists are exploring new materials such as graphene and other two-dimensional semiconductors that could offer even better performance. Advanced doping techniques like atomic layer deposition are being developed to create ultra-thin and precisely controlled layers. These innovations could lead to faster, more efficient, and more powerful electronic devices in the years to come. Doping processes can have environmental impacts, such as the use of hazardous chemicals and the generation of waste. The semiconductor industry is working to minimize these effects by developing cleaner processes and recycling materials. Sustainable manufacturing practices are becoming increasingly important as demand for electronic devices continues to grow worldwide. Ensuring the quality of doping is critical for device performance. Manufacturers use advanced testing and inspection techniques to check the concentration and distribution of dopants in each wafer. These quality control measures help prevent defects and ensure that every device meets strict performance standards, contributing to the reliability of modern electronics. Doping is not just important in manufacturing, it's also a key area of research. Scientists are constantly experimenting with new dopants and doping techniques to improve device performance. Research in this area has led to breakthroughs in fields like quantum computing, flexible electronics, and high-efficiency solar cells, pushing the boundaries of what's possible with semiconductors. Quantum computing is an emerging field that relies on precise control of materials at the atomic level. Doping plays a crucial role in creating the quantum bits, or qubits, that store and process information in these devices. By carefully selecting and placing dopant atoms, researchers can create qubits with the properties needed for quantum operations, opening up new possibilities for computing. Flexible electronics, such as bendable displays and wearable devices, also benefit from advances in doping technology. By developing new dopants and doping methods, engineers can create flexible semiconductors that maintain their performance even when bent or stretched. This opens up exciting new applications for electronics in healthcare, fashion, and beyond. Doping is a key factor in the development of high-efficiency solar cells. By optimizing the type and concentration of dopants, researchers can improve the ability of solar cells to convert sunlight into electricity. This leads to more efficient and cost-effective solar panels, helping to accelerate the transition to renewable energy sources. Vibrant colors and brightness of modern LED displays are made possible by precise doping. By adjusting the dopants in the semiconductor material, manufacturers can produce LEDs that emit specific wavelengths of light. This technology is used in everything from televisions to smartphone screens, delivering stunning visuals and energy-efficient performance. Doping also plays a role in data storage technologies such as flash memory and solid-state drives. By creating regions with different electrical properties, doping enables the storage and retrieval of digital information. Advances in doping techniques have led to faster, more reliable, and higher-capacity storage devices, supporting the growth of the digital world. Modern communication devices such as smartphones and wireless routers rely on doped semiconductors to process and transmit signals. Doping allows these devices to operate at high speeds and with low power consumption, making fast and reliable communication possible. This technology is at the heart of the connected world we live in today. Medical devices such as pacemakers and diagnostic equipment use doped semiconductors for precise control and monitoring. Doping enables these devices to operate reliably and accurately, often in life-critical situations. Advances in doping technology have improved the performance and safety of medical electronics, contributing to better healthcare outcomes. Automotive electronics, including sensors, control units, and power systems, depend on doped semiconductors for efficient operation. Doping allows these components to handle the harsh conditions found in vehicles, such as temperature extremes and vibrations. This technology is essential for the safety, performance, and reliability of modern cars. Internet of Things, or IoT, connects billions of devices worldwide, from smart home gadgets to industrial sensors. Doped semiconductors are at the core of these devices, enabling them to process data, communicate, and operate efficiently. Advances in doping technology are helping to make IoT devices smaller, smarter, and more energy efficient. Artificial intelligence systems require powerful and efficient hardware to process vast amounts of data. Doped semiconductors are used to build the high-speed processors and memory chips that make AI possible. By optimizing doping techniques, engineers can create chips that deliver the performance needed for advanced AI applications, from voice recognition to autonomous vehicles. Security devices such as biometric scanners and encryption hardware rely on doped semiconductors for fast and secure operation. Doping enables these devices to process sensitive information quickly and accurately, helping to protect data and ensure privacy. As security becomes increasingly important, advances in doping technology will continue to play a vital role. Wearable technology, such as fitness trackers and smartwatches, uses doped semiconductors to deliver powerful features in a compact form. Doping allows these devices to process data, connect to networks, and operate for long periods on a single charge. This technology is driving the growth of personal health and fitness monitoring. Energy efficiency is a top priority in modern electronics. Doping allows engineers to design devices that use less power while delivering high performance. This is especially important for battery-powered devices such as smartphones and laptops, where longer battery life is a key selling point. Advances in doping technology continue to improve energy efficiency across the electronics industry. Reliability is crucial for electronic devices, especially those used in critical applications. Doping helps ensure that semiconductors operate consistently over time, even under challenging conditions. By carefully controlling the type and concentration of dopants, manufacturers can produce devices that are both durable and dependable. Doping not only improves performance but also helps reduce the cost of electronic devices. By enabling the use of smaller and more efficient components, doping allows manufacturers to produce more devices at lower cost. This has made advanced technology accessible to more people around the world, fueling the growth of the digital age. One of the great advantages of doping is the ability to customize the electrical properties of semiconductors for specific applications. By selecting the right dopants and concentrations, engineers can design devices with exactly the characteristics needed for each use case. This flexibility is key to the diversity and innovation seen in today's electronics. Sum up, doping is the process of adding impurities to semiconductors to control their electrical properties. This simple yet powerful technique is at the heart of modern electronics, enabling everything from computers and smartphones to solar panels and medical devices. By mastering the art and science of doping, engineers have unlocked the potential of semiconductors, shaping the world we live in today. As we look to the future, doping will continue to play a vital role in the evolution of technology. With ongoing research and new discoveries, the possibilities for semiconductors are nearly limitless. Whether it's faster computers, cleaner energy, or smarter devices, doping will remain at the core of innovation, powering the next generation of breakthroughs.